All right, so here we go. So 6.6. All right, so you don't necessarily have to write this screen down. We've already talked about domain, but I just want to address it one more time. So domain represents all of those inputs that result in a real answer. Okay, so if my domain, if I put in -2, and what I'm trying to do is take the square root of -2, it fails. So really -2 would not be in my domain. So now we're going to look at restricting that domain in order to get answers. All right. Another thing to watch out for, can't divide by 0. So say we had some fraction and say we had x plus 2 all over x plus 7 was our function. Well, I know on this one, x cannot be a -7 because if I put -7 in there, I end up with 0 in my denominator and I can't divide by 0. Okay, so our domain can now be restricted. We could say, okay, any number will work for x except -7. And then we'll look at how we can write that as a solution set, that x can be any number, but it can't be -7. Okay, and again, square root. Okay, so say we're just working with the basic square root function. On this one, we know we can only go from 0, 1, 2. We're only going positive. So x cannot be any negative numbers. Okay, and this happens for any even root. I could have the 16th root of x. Because that index is an even number, I can never take an even root of a negative number. So that's going to restrict my domain as well. Okay, all right, so let's take a look. If I want to know, these ones I'm trying to identify, well, what is the domain? F of x equals x squared minus 6. We're only looking domain. We're not talking about range or anything on these examples. We're only looking at, is there any restrictions on the domain? Okay. What about just a quick graph to see visually what's going on? X squared minus 6. What's the graph of x squared minus 6 look like? What about x squared? Sterling, what's an x squared graph look like? Parabola opening up or down? Up. What's that minus 6 doing to our parabola? Sterling. Keep going. You're on the right track. Okay, so it intercepts down here. So this -6 is going to be the vertex of it. So, yep, I know what you're saying, but it's shifted down 6 units essentially. All right, so our domain for this one, what possible x values could I put into this? Can I put in -150? If I went way out here to -150, it will eventually touch on my line here, because that line is going to keep going. I could go all the way out to a positive million. Okay, I'm way out here at 1,000,000. That's going to work. Okay, so how can we represent our domain being anything? Kevin, what do you say? You could literally write out all real numbers. You could use our fancy R with 2 vertical bars. You could write it in interval notation of -infinity to infinity with parentheses around it. This example 1 has no restrictions. I could put any x value. I know my range is going to be limited. My range is only going to go from -6 at the smallest all the way up to infinity, but we're not talking about range right now. All we're talking about is domain. Okay, example 2. So I already talked about this one. What's the limitation if I have a square root function, or if I have an even root function? Can I take the square root of -0.1? Nope. Okay, so this one, I could say in interval notation from 0 all the way to infinity. Would I put a bracket or a parenthesis around the 0? Is it inclusive or not inclusive? Can I take the square root of 0? Square root of 0 is something I can do. Ethan, what do you say? No? Colin, what do you say? You don't think so? Marcus, what do you say? I don't think so. Ben, what do you say? Okay, there's a reason I keep asking this. Max, what do you say? Square root of 0. Yeah, square root of 0 is 0. Okay, so that's allowed. Okay, square root of 0 does equal a number which is 0. So this is inclusive. Okay, so it starts at 0, and if we were to graph this, it has a point there at the origin, and then it continues up like that. So square root of x looks like that. All right, so square root of 0 is allowed. You can take the square root of 0. You can't take the square root of any negative value, though. Then the third example here, x squared plus 4 all over x minus 1. Are there any restrictions to my domain for this one? Yes. Okay. What do you say? Avery? Not Avery. Yeah. Okay. What about -1?
Well, it's
Correct. So x cannot be 1. Okay. Another way, so we could say all real numbers, comma, x cannot be 1. You could write this in interval notation as well. I could say from -infinity all the way to 1 with a parenthesis around the 1. So this is going to take into account all my negative numbers, 0, all the way up to 1, but I'm not going to include 1. And then we have this U symbol that stands for union, kind of like an and. So my interval is from -infinity to 1, and from 1 non-inclusive all the way to infinity. So you can represent it that way. Either one works. If you say all real numbers, comma, x cannot equal 1, I'm good with that. If you write it in interval notation, I'm good with that. If you literally wrote it out in words, can be all real numbers except 1, that's fine. Okay, but we cannot have 1 as a part of our domain. Now, next thing, function operations. So I'll give you a minute to write these down, and these are very straightforward. If I have two functions that are added together, and it might make more sense to think of it from the right side going to the left, but that equal sign says it can go both directions. If I had two functions that I'm adding together, I could simply add them together and take them as a function of x. Okay, so just how they're written, addition stays addition, subtraction stays subtraction, multiplication is multiplication, division is division. We'll do some examples to clarify how these work. And you can see on the last one with division, it says g of x cannot equal 0. Again, we can never divide by 0. So we always need that numerator, or I'm sorry, the denominator, to be a number. It can be a negative number, but it simply cannot be 0. That's I knew when I said it was wrong. I thought you were going to correct me. Okay, so again, these are just all the rules, and there's no tricks here. I mean, it's just addition stays addition, but you can break them apart. Subtraction, multiplication, division, you can just break them all apart. But they do go both directions, and we'll do some examples to help clarify. All right, now, when doing function operations, the domain is affected, and we have to pay attention to domain. So the domain after a function operation is whatever values are in the domains of both f and g. Okay, so we have to look at the domain of everything. If it fails in one, that is excluded from the domain of your final answer. Okay, because we're going to work through algebra and we're going to come up with a new function, and you're going to be tempted to look at that and you're going to see something like, nope, it can't be this number. But then we have to look back at what the originals f and g were to make sure there was no restrictions on that. Because if the domain wasn't in the original f, it can't be in your final answer. Okay, and f and g, it doesn't make the denominator equal to 0. Okay, so for this example, if f of x equals x plus 2 and g of x equals x minus 5, so we're just working with two different functions. Let's first identify the domain of each of these. Are there any restrictions to my domain for the function f? Is there anything x cannot be? And the red flags are if you have a fraction, there's going to be restrictions. If you have a square root, there's going to be restrictions. If it's strictly a linear function like both of these are, no restrictions. Okay, so division or square roots, that's when red flags should go up. Okay, I'm going to be restricted. So this one's actually all real numbers, and this one's all real numbers too. So there's nothing from the start that's going to restrict what our final domain is after we add these two functions together. All right, so f plus g of x is what we just saw in that last slide. That's taking f of x plus g of x. Okay, so f plus g of x, we can split it up. And then all that's going to be, well, my f of x was x plus 2. And I'm adding, so I'm going to add x minus 5. And if you want to put them in parentheses, oftentimes it's helpful to put them in parentheses because when we get into subtraction of functions, that subtraction is going to play a part. When you subtract, say, a negative, it's going to turn into addition. So from the start, if you just put them in parentheses, that's going to help you keep organized and you don't make a little mistake. Okay, so x plus 2 plus x minus 5. Okay, well, x plus x is going to be what? What's x plus x? 2x. Okay, don't get, we were doing all that stuff with exponents. Don't think it's x squared. Okay, if I had one apple and I had another apple, I have two apples. I don't have apples squared. Okay, so this is 2x. And then my numbers, 2 plus a negative 5 is negative 3. So my new function, adding these two functions together, I create 2x minus 3. This is a whole new thing. Okay, I started with these two pieces, I combined them, now I have 2x minus 3. My domain on this one, it's linear. There's no square roots I have to worry about. There's no fractions I have to worry about. This is just all real numbers. Or if you wrote an interval notation, negative infinity to positive infinity. Same thing. There's no restrictions on this one. But now division. Okay, so division, we're going to have some restrictions. Our initial functions, f of x and g of x, don't have any restrictions, so we know just our final answer is all we have to worry about. So again, this is f of x divided by g of x. So this function just becomes x minus, x plus 2 divided by x minus 5. There's no simplification. There's nothing fancy we have to do with that. It's simply x plus 2 divided by x minus 5. That is the division of these two functions. But now my domain is restricted. I know I can have any number I want except x cannot be a positive 5. Right? I could go negative 1,000,000, I could go negative 10, I could go positive 100. Any number I want to choose except x cannot be 5. All right, let's do a few more. So we're going to start out with f of x being x plus 7. But g of x is a quadratic, x squared plus 9x plus 14. We want to find each function operation and the domain. The domain of our final function that we have. So first off, we want to look, okay, what's the domain of our original? X plus 7, I could have any number into that. And then my domain of x squared plus 9x plus 14, we know that's a parabola opening up, but domain could be all real numbers as well. So I don't have any restrictions on my f of x or g of x, so that's good. All right, so if I want to add these together, I have x plus 7 plus x squared plus 9x plus 14. Adding them together, all I'm doing is combining like terms. And so this would be x squared plus 10x plus 21. All I'm doing is combining like terms. Addition's very straightforward. My new sum or addition of functions creates x squared plus 10x plus 21, which is a parabola. My domain of that one is all real numbers. There's no restrictions on that, and there were no restrictions on f of x alone or g of x alone. So that's why I can just say, yep, any number will work. I can put any x value. Next one with subtraction. So that's why I say parentheses are often helpful on this. I have x plus 7, but then I'm subtracting x squared plus 9x plus 14. So we can think that that negative is actually being applied to every single one of these terms. So when I do this one, I have x minus 9x, and so that's a negative 8x. X squared is by itself, but it's a negative x squared. And then 7 minus 14 is negative 7. Okay, so that negative is going to apply in every single term. In this one, I don't have it, but if it was x squared minus 9x, and I'm subtracting, it's going to be a minus, a negative, so it's going to change to addition. So be very careful on subtraction ones. Oops. With this one, I still end up with a quadratic. It's a negative x squared. All it means it's opening down, but it's still all real numbers. All right, multiplication. So this is going to be a fun one because we have x plus 7, a binomial times a trinomial. So this one's going to get long. We're going to use our distributive property, and we have to take our initial x and the x plus 7 multiplied 3 times through, our 7 multiplied 3 times through. So now multiplication, x times x is x cubed. So we're multiplying now, we're not adding. If I have an apple and I multiply it by another apple, I have apple squared. If I added them, I'd only have 2 apples. So I have x cubed plus 9x squared plus 14x. And then I got to do this again, but with the 7. So 7 times x squared, 7x squared. 7 times 9x, positive 63x. 7 times 14 is going to be a positive 98. From here, I can combine like terms. I only have 1x cubed. I'm going to mark that off so I don't forget, or so I make sure I've taken that into account. 9x squared and 7x squared is going to give me 16x squared. Those are gone, that's gone. 14x plus 63x, that should give me 77x. Cross those out, plus 98. So that's my multiplication of the two functions. And again, domain and range on this one, or sorry, just domain. Domain, this is a cube. That's fine. A cube, any cubic function, looks like some variation of that. Yeah, I can have any x value. There's not going to be any limitations on this. So this is all real numbers. And then this last one. So this one's the most fun. F divided by g, I want to do f of x as my numerator. So this is x plus 7 on top. G of x would be x squared plus 9x plus 14. I need to identify, are there any x values there in my denominator that won't work? Is there any restrictions on that? This one, oops, let's actually factor that bottom. So we do a quick cross, two numbers multiply to get 14, that add up to be 9. I know I could do 7 and 2. And so my numerator still stays the same, x plus 7, but my denominator now is x plus 7 times x plus 2. Now it's very apparent that these x plus 7s go to a useful form of 1. Do not say cancel. If I hear you say cancel on this, I'm going to correct you and I'll say don't say cancel. They don't cancel. They're still in there. All it is a multiplication by 1. So I have 1 times in my denominator x plus 2, or 1 over x plus 2. So that is the division of these functions. Now, my domain. So we're working with division, so we know there's going to be some red flags going on. I need to look all the way through the problem and see if there's anywhere that my domain is restricted by the denominator. Well, this one's easy to see. I know x cannot be a negative 2, okay? Right there, my final answer. I know x cannot be negative 2. As I work backwards, though, this x plus 7 in the denominator is still there. Like I said, it went to a useful form of 1. That didn't go to 0. That went to a useful form of 1. That's still there. And so x also cannot be a negative 7. Outside of those, I could have any real number. So a complete answer to this, I want you to say the domain, I can have any real number except x cannot be negative 2 and x cannot be negative 7. So we have to keep looking backtrack through our problem, see if there's anywhere that we ran into these snags. Now, composition of functions. So this is where we turn it up a notch. Okay, and it's all in understanding the notation. So as long as you understand that notation, you're good. The actual work is not hard. The math is not hard. Where students mess up is the notation, understanding which goes first, what they're doing, what order it goes in. Okay? This little open circle, that means composition. Do not confuse that with multiplication. All right, an open circle, and it will be a distinct open circle. That means composition. All right, if you look back when we were doing multiplication, it was definitely filled in dots. So F, this is read as F of G of X. So right here, same thing here. I would read this as F of G of X. That's how we would say that. How we attack a composition of functions is always start on the inside and work backwards, or you can think of working left, whatever way makes the most sense to you. And when I say inside, I'm going inside my parentheses as far as I can go. So sometimes you can think it is inside out. Start with the inside and then work out. So for an example, if we had two functions that we wanted to do a composition, composition just means compose. We're going to compose two functions together. If f of x is x squared, and just for practice here, we know our domain on this one's going to be all real numbers. Our domain on this one is also all real numbers. And we want to compose this with an x value of 5. So where it says find f of g of 5 is what that's saying. So first off, we want to attack this g of 5. And g of 5 is going to come right from here. So g of 5 is 2 times 5 minus 7. So 2 times 5 is 10 minus 7, and we get 3. So now I'm going to rewrite this composition, okay? And I'm doing it for visual reference here to help you show what's going on, okay? You don't. So really, I was taking f of g of 5. Well, I know g of 5 is 3. So I can replace that g of 5 with just the number 3. And now all I have is f of 3. So f of 3 will be 3 squared to be 9, and that's my final answer. So a composition of these two functions, first I have to figure out what g of 5 is, figure out that number for g of 5, put that in to become f of 3, and I end up with 9. Okay. Let's do some practice with these. So two functions, x minus 5 and x squared plus 2. That's the last slide we're going to do. So we have two functions and we are going to compose, meaning we're going to put these two functions together. They're not being multiplied, they're not being added, subtracted, divided. They're becoming one. They're being absorbed into the other. So f of x is x minus 5, g of x is x squared plus 2. You notice the first two lines, it says g composed with f, and then f composed with g. Order is important. Those mean different things. Okay, so g composed with f, if we want to think about that, this one we could write out, and we could say g of f of negative 3. That's the same thing. In this notation, a few other math teachers here will say golf or fog. This still, you do this, and then you do this. So you take it kind of from the right side in this notation, working left. All right? Either notation, they both mean the same thing. So what this is saying, well, first we got to figure out what f of -3 is. And so that would be a -3 minus 5 to become -8. So now I'm going to write g, instead of writing f of -3, I know that's -8. So it's g of -8, which becomes -8 squared plus 2 to end up with 66. All right, so work from the inside, get that new number, replace your f of -3 in your composition statement with that number, and then do the operation one more time. Now, switching it up, saying f of g of -3, that's saying f of g of -3. So first thing I want to figure out, okay, what is g of -3? That would be -3 squared plus 2. So 9 plus 2 to get 11. Now I'm going to do f of this new number that I found, just f of 11. So f of 11 would be 11 minus 5 to end up with 6. And there's our final answer. Right, so that initial input that they give you, in our case was -3, put that into the first function, get a number, put that new number into the next function. All right, and then again, just practicing with notation, this f of g of 5, first I got to figure out what g of 5 is. And so that would be 5 squared plus 2 to end up with 27. Now I'm going to do f of that new 27 that I found. So 27 minus 5 to end up with 22. All right, but order is important. Work inside out. If it's in the golf or the fog form, right to left. Do the right piece, plug that in for the left piece. And then the last one, it's not a typo, g of 10. So the first thing I want to figure out is that inside piece. Okay, what's g of 10? So that'd be 10 squared plus 2 to end up with 102. And then I'm going to take that new number and I'm going to do g of 102. So this would be 102 squared plus 2. So 10,406 would be this final answer. All right, so again, order. Make sure you know the order. If it's with parentheses, like the third example there, f of g of 5, inside out. If it's with the golf or the fog form, right to the left. Okay, all right, so your homework, page 409, 21 through 26, 9 through 14, 21 through 26, 27 through 41, just the odds on that set, 74, 76.